Okay, so average rate of change. That's what we talked about last time. We're going to see average rate of change again today. So a little review, but also some sort of different kind of context, a little bit different spin to a few of our questions for today. This table should look familiar because we worked on this last time. This was, I think, example 2 from last time. And I want to start with where we were working yesterday. Again, if you were gone yesterday, this is a good, really quick review. So if I want to find the average rate of change for the price of gas from 2005 to 2008, that means I am looking at the price of gas in 2005, the price of gas in 2008. I am treating those as if they are ordered pairs. And then I'm finding the slope between those 2 points. Okay. This is a non-linear function. I can tell because my y values, my output values are going up and then down and then up again. And when they go up by different rates. So I know that this isn't linear. I know that I couldn't describe this with a line. So that's why I'm not saying find the slope. I'm saying find the average rate of change. We're saying what's the average amount that we're changing by over this interval of time. So if you are a labeler, x1, y1, x2, y2, and then remember our slope formula is y2 minus y1 over x2 minus x1. So for this problem, we would have 3.30 minus 2.31 over 2008 minus 2005. On top, we get 0.99. On bottom, we get 3. And then based on the context of this problem, I'm going to go ahead and divide this out, and we would get 0.33. If this looks familiar, it's because this was example 2 from last time, okay? And so then we talked about what does this mean in the context of my problem. So what this is telling me is that on average, the price of gas rose or increased, since this is a positive value, that means it went up, increased by an average of 33 cents per year from 2005 to 2008. And then we talked yesterday about how it's never for these periods exactly 33 cents. This one's pretty close at 31 cents. This one's a little less. This one's a little more. The average is 33 cents. So we have the difference between those years over that time frame divided by the amount of years that we had that gave us our average rate of change. Now we're going to do this again, but with a different time frame. So this time, 2006 to 2010. So here's 2006, here's 2010, exact same idea. So I'm going to treat these like points, 2006, comma 2.62, and 2010, comma 2.84. Again, if you like labeling x1, y1, x2, y2, and we find the slope between those 2 points. 2.84 minus 2.62 on the top, and on the bottom, 2010 minus 2006. So on the top, we have a difference of 22 cents. And on the bottom, this is over a period of 4 years. So when we divide here, we get 0.055. Now, in the context of our problem, it doesn't make sense to take this to 3 decimal places, right? Because we're talking money, so we need to round to the nearest penny. So we're going to say this is 0.06 or 6 cents. So that means on average, over this 4-year period from 2006 to 2010, the price of gas increased an average, again, this is an average, of 6 cents per year. Okay, so that's the difference between these two values, where I started and where I ended. Now, if I look at all the changes in between, none of them are 6 cents, right? This is 22 cents, I think. This is a bigger change. Then we drop really steeply by almost $1, and then we're creeping back up by a little over 40 cents. But the difference between my starting and ending point is about 6 cents per year that we have changed. Now, it doesn't mean the difference between this number and this number is 6 cents. Bless you. It means about 6 cents per year is how we could get from here to here. Okay, average rate of change. What I would like you to do now is to find the 1 year period that had the greatest average rate of change. Okay, so for 1 year period, I mean like 2005 to 2006. What was that change? 2006 to 2007. What was that change? 07 to 08, and so on and so on. So over a 1 year time span, which 1 year period had the greatest change? The nice thing about looking at 1 year intervals is that your bottom is going to be 1 each time. So you really just need to focus on the difference in those prices. Check your work. Which 1 year period had the greatest change? 2008 to 2009. That was the biggest change. Notice this says change, not greatest amount of money, right? That was like greatest increase, not greatest value here, I should say. Okay. So when we say change, that could be negative too. It could mean it decreased in this case for our price of gas. Okay. Which 1 year period had the smallest change? This was, yeah, this was our greatest change. This is our smallest change. Here's kind of where we're going to look at this in a little bit different lens for today. Okay. We're going to talk about intervals when we expect our function to be increasing or decreasing, okay, based on that rate of change. So I want you to remember that we read graphs from left to right. And when we talk about a graph increasing, that means we are going up as we move from left to right. When we talk about a graph decreasing, that means we are going down from left to right. So if we think about our rate of change, remember what we were calculating there was essentially slope, right? So if we think about the rate of change, what kind of rate of change, what kind of slope would I expect if we're increasing? What kind of number? Positive, negative, positive, right? What about if we're decreasing? What kind of rate of change would I expect there? Negative. So still using our data from that table at the top of the page, what would be an interval of time where our price of gas was increasing? There are a lot of correct answers here. So give me a time frame. From this year to this year, we're increasing. 2010 to 2011, sure. We could also say 2010 to 2012. We could do more than 1 year. Okay, increasing. The price is going up. If we go earlier, 2005 to 2006, 2005 to 2007, 2005 to 2008 even. And we don't have to start at 2005. From 2006 to 2008, that price is also increasing. So there are a lot of different options here. What about an interval where we're decreasing? What's an interval of time where we're decreasing? The price of gas is decreasing. Yeah, right. You just won for that one, right? 2008 to 2009. Price is definitely decreasing from 2008 to 2009. If I looked at a longer interval and talked about the average rate of change decreasing, then I could maybe expand that a little bit. 2008 to 2010, the earlier year is greater. The price of gas is greater than the later year. Okay. But much more limited on my options for part B. So this is kind of the expansion for today, extension for today. Question for me so far? Go ahead and turn the page. At the top of our next page, example 2, it says the electrostatic force measured in newtons between two charged particles can be related to the distance between the particles d measured in centimeters by this formula. Now, I'm going to stop right there before I finish reading this problem. This is the kind of problem that the SAT likes to ask you because they know you look at it and go, newtons, charged particles, and then your eyeballs like roll around in your head a little bit and you're like, I don't think so. Moving on. Next question. It's probably B, whatever. Okay. I want to point out that these word problems that have all this like context, you don't need any of this to be able to answer this question. Okay. This is a rate of change problem. It gives you the function and it tells you the interval. Find the average rate of change from 1 to 4. That's all you need from here. Okay. This is a problem that you can do. So when you get something like this on the SAT, don't like freak out about all the like context and directions. It is just average rate of change, which you guys can do. Okay. Now we looked at some problems yesterday where we found an average rate of change when we were given a function. And the only like really extra part of these, the only thing that made these a little trickier is that we had to actually go find what the y value is for the points. On a graph or a table, I can just see the x and y together. But when I'm given a function, I have to find them. So that's the only thing that makes this one a little more work. Is I have to find f of 1, and then I have to find f of 4. So remember, this means I'm plugging 1 in for d. So 2 over 1 squared. Well, that's 2 over 1, which is just 2. So my first point is 1 comma 2. And then for my second point, I'm plugging 4 in for d. So 2 over 4 squared, which would be 2 over 16. And we can reduce that to 1 over 8. So my second point is 4 comma 1/8. Now that I've got 2 points, I plug these in to my slope formula. So this would be 1/8 minus 2 over 4 minus 1. On top here, in order to subtract, I'm going to need common denominators. So this would be 16 over 8. So I get negative 15 over 8. Not our prettiest value we've ever had, but that's okay. And then on the bottom, we get 3. If you were going to type this in your calculator at this point, that's fine. I don't have one handy in front of me right now, so I know that if I divide fractions, I'm multiplying by the reciprocal. I'm going to reduce that way. This would be -5 over 8. Again, if you changed it to a decimal, that's fine too. But just average rate of change. All this extra stuff in here doesn't matter. It's just average rate of change. Questions for me on example 2? Example 3, part A, straightforward average rate of change. I could have given you part A yesterday. So let's start by finding f of 0 and f of 4. So we're going to plug in 0 for x. That'd be 0 squared plus 3 times 0 plus 1. So that's 0, that's 0. This is just 1. We have the point 0, comma 1. And then when we plug in 4, we have 4 squared plus 3 times 4 plus 1. So that's 16 plus 12 plus 1. This is 28, 29. My other point is 4, comma 29. And now I find the average rate of change. Again, if you like to label your points, x1, y1, x2, y2, if that helps you, make sure you put everything in the correct spot. That's absolutely fine. This would be 29 minus 1 over 4 minus 0. So we get 28 over 4, which is 7. So for this function, f of x, over the interval from 0 to 4, our average rate of change is 7. B, a little bit different. Again, this is something that SAT likes to do. Instead of giving you numbers here, they like to throw in constants where they don't actually tell you what the value is. That's okay. That doesn't change anything that we're doing here. And I already plugged in 0, so I already know the first point is 0, comma 1. Let's plug in A now. So anywhere I see an X, I'm going to plug in an A. There's nothing to simplify here because they didn't actually give me a value for A, so I'm just going to keep it as A. That makes this point a little odd, but nothing that we can't handle. And then I've got x1, y1, x2, y2. y2 is clunky, but that's okay. Then when I go to find my average rate of change, a squared plus 3a plus 1 minus 1 over a minus 0. We simplify as much as we can. On top, the only thing I can really simplify is plus 1 and minus 1. So I have a squared plus 3a. And then on bottom, a minus 0 is just a. There is one more thing I can do to simplify here. I have a GCF on top. Raise your hand if you remember talking about GCF last year in Algebra 1. I should see everybody's hand up. We did GCFs for like 100 years last year. Yeah. Okay, GCF of A here. Factor that out. And then I can reduce that A. So our rate of change here is just A plus 3. I want you to notice that this actually fits. This answer we got for part B fits with what we found for part A. So what this is saying is if you go from 0 to some other number, you should end up with just that number plus 3 as your rate of change. So for part A, we went from 0 to 4. 4 plus 3 is what we got here. Questions for me on 3? I'm not going to give you a ton of problems like B, But I did want to work through one together with you guys since I know you're likely to see something like this on SAT. Maybe not an average rate of change problem, but something where they don't give you an exact value. They give you a stand-in constant, okay? For example 4, we're looking at a graph again, but this time I'm not actually asking you to find a rate of change for anything, okay? I'm just asking you to give me intervals where we expect our rate of change would be positive or negative. So describe an interval where the average rate of change is positive. So we talked about this on the last page, right? When my rate of change is positive, that's a section of my graph where we're increasing as we read from left to right. When my rate of change is negative, that's a section of our graph where we're decreasing. So there's not one correct answer here, but if I look at A, describe an interval where the average rate of change is positive, okay, where my rate of change is positive, that means that we are increasing. So I should be going up from left to right. Remember, we describe intervals based on their x values. So for example, I might say I have an interval from -1 to +1, where my average rate of change I expect to be positive because that section of my graph is increasing. So I could say I have an interval from -1 to +1, where I expect that rate of change to be positive. What would be another example of an interval where a rate of change would be positive? There are lots of options here. Another section of our graph where that rate of change would be positive. From 4 to 5, sure thing. It also continues to be positive for the rest of my function. So I could even expand that and say from 4 for the rest of the graph, right? From 4 to infinity. I could take the interval that I started with and break it down. I could say from -1 to 0. I would also expect that rate of change to be positive. Or from 0 to 1. Or from -0.5 to +0.5. What about an interval where the average rate of change is negative? So that means we have to be decreasing. -3 to -2? Sure thing. Give me one more. Anybody? From 3 to 4? 2 to 3? So from 3 to 4, from 2 to 3, jot these down. 3 to 4, 2 to 3. I could also say, so we said from -3 to -2, but since we're decreasing the whole way, we could also say from negative infinity until 3 or even -2. Okay. As long as I'm looking at a section where we're decreasing. And then what about an interval where that average rate of change is 0? We saw a couple examples of that yesterday. Our average rate of change was 0 when we had 2 points that were at the same y value, 2 points that were at the same y. Gave me something that was horizontal. Thank you. What about from -3 to 2? Horizontal, 0 change? Yep. You could also do from 2 to 5 or from -3 to 5. I don't have to pick values that are on the axis either. I could also say from, let's say 1 to 3. It looks like it's about the same there. right? 1 to 3, that looks like it would also make a horizontal line. Even though those aren't super nice points, they're not nice y values, still makes a horizontal line. Questions for me on increasing, decreasing, and average rate of change? Okay. Just a couple more examples for today. Turn the page for me, please. For example 5, we have 3 functions represented here in 3 different ways. So we have a graph, we have a function, we have a table of values. I want to find the average rate of change for all of these over the interval from -4 to 5. And then I want to order the functions from least to greatest based on that rate of change, okay, based on how much we're changing. So I'm going to start by identifying my points for this interval on f of x. I'm going to start with f of x. I know our grid lines are kind of faint here, but this would be the point -4, 25, I think. And then at 5, that would be here, so 5, 0. So my average rate of change between these points would be 0 minus 25 over 5 minus -4. So that gives me -25 over 9. If we want to change that to a decimal, that's going to be about -2 something, not quite -3. Somebody want to double check, but I think it's like 2.7 something. Someone divide that for me and double check me. 2.7-ish. Okay. So for f of x, our rate of change is -2.7. Let's do g of x next, because I can find my points pretty easily from my table. So -4 and +5. My rate of change then would be 8 minus 98 over 5 minus -4. So that's -90 over 9, which is -10. So for g of x, our rate of change is -10. And then h of x is going to be our most work here. I'm going to look at this one down here, because I have to actually go find the y values. So I need to start by finding h of -4. That would be -4 squared minus 5 times -4 plus 42. So that's 16 plus 20 plus 42, which would be 78. And then h of 5 would be 5 squared minus 5 times 5 plus 42. So that's 25 and that's 25. Since we're subtracting them, I'm just left with 42. So I need to find the rate of change between the points -4, 78, and 5, 42. So this would be 42 minus 78 over 5 minus -4. So we get -36 over 9, which would be -4. So for h of x, our rate of change is -4. Now I asked you to order these from least to greatest according to the amount of change that we're having here, the amount of change. So for which of these functions do we change the least? Which of them we're changing the least? f of x, we're changing the least, right? If I asked you to order them according to their values, right? The like numbers that you got, this is actually the biggest of the numbers if I think about a number line. But if I'm talking about amount of change, f of x is my smallest change. What's our next smallest change? H of x. And then our greatest change was g of x. We changed by 10. We were going down by 10, but we changed by 10 there. Now I will tell you, I believe I gave you an assignment on Delta Math that asks you to order based on this, but they want you to order based on those actual values, not the amount of change. So be careful with your directions on those problems. And then last one for today, we're doing some comparing again. We've got a graph this time, and we're looking at different intervals on the same graph. So when we talk about amount of change, another way that we can think about that, especially if we've got something visual to look at, if we have a graph like we do for example 6, is what's the steepness of the slope? Remember, amount of change is going to be related to that steepness of our slope. How far am I going up or down? So we could go through and calculate slope for all of these. But for this last example, I want to talk about steepness. Okay, I want to look at that comparison kind of visually. So the first few are just these different segments of my graph. From 6 to 14, I'm going to call that 1. From 14 to 32, from 32 to 53, and from 53 to 89. So for these different segments, which of them is the steepest? Which of them has that greatest amount of change? 1, 2, 3, or 4? Which of these sections is the steepest? 1 is the steepest of these. So I'm looking for on which interval is the rate of change the greatest. So 1 is the steepest so far. That's A. So I'm going to get rid of B, C, and D. And then the rest sort of combine some of these different sections. So E is from 6 to 89. That's the whole thing, from 6 to 89. Let me get I'll sketch these in some different colors so we can look at this a little better. From 1 to 89, what's steeper, 1 or what I've drawn in pink here? 1 is still steeper, so it's not E. And then let me change colors again. 14 to 53, so that's from here to here. What's steeper? 1 still, right? And then for our last front one, from 6 to 32, that's here. What's steeper, 1 or my line here in green? 1 still. So that section should have my greatest rate of change. Right? It's got the steepest slope. That is it, you guys. We made it through all of our content for our first unit of Algebra 2.